This is the Earth, and we want to put a satellite in a geostationary orbit. What does it mean to say that the satellite is in a geostationary orbit? Let's say there is a city right here on the equator, and we wish to put a satellite right above that city, and we want it to be in an orbit so that the time period of the orbit is 24 hours, the same time period of rotation of the Earth, so that at all times this satellite stays right above the same city. So people in this city, when they look up, they will see a satellite overhead, and as the Earth rotates, the satellite will continue to stay overhead. So let's write down the equation for that. The gravitational pull on the satellite is going to be Newton's universal constant g, mass of the Earth, mass of the satellite, divided by square of the radius of the orbit. Now this force provides the requisite centripetal acceleration. So this is equal to mass times the acceleration of the satellite, and instead of writing v squared by r, let's put it in the form r omega squared. Omega is the angular velocity of the satellite. Now we want the time period of revolution of the orbit to be 24 hours, which is so many minutes multiplied by another 60 to get so many seconds. And omega is 2 pi by the time period. And what else do we have? G is approximately 6.7 times 10 power minus 11 Newton meter squared per kilogram squared. And the mass of the Earth again is approximately 6 times 10 power 24 kilograms. Mass of the satellite, of course, cancels, as it happens in every gravitational problem. Why? Because the orbit of any object in a gravitational field is independent of its mass. Again, it goes back to Galileo: a feather and a cannonball drop together. So if we substitute all these numbers and calculate r, I leave the calculation to you. R turns out to be approximately 42,000 kilometers. That's the radius of the geostationary orbit. Now, since the radius of the Earth is about 6,400 kilometers, you can subtract that from 42,000 to get the height of the satellite above the city. Since the radius of our geostationary orbit is about 6.7 times the radius of the Earth, the drawing looks more like this than the previous one. Our satellite is out here in the geostationary orbit. But here is a question. Can we put a satellite in a higher geostationary orbit? That is, supposing we want the radius to be, let us say, instead of 42,000 kilometers, supposing we want it to be 50,000 kilometers, is it possible to put a satellite in a geostationary orbit? That is, the time period still being 24 hours. So let's draw that orbit. So here we have the satellite in a larger radius orbit. How do we make this orbit geostationary? Going back to this equation, g, mass of the Earth, mass of the satellite divided by r squared is equal to mr omega squared. We want omega to remain the same, that is the same 24-hour time period, but we want to increase the radius. So the right hand side increases, and if you look at the left hand side, it actually decreases because the radius is increased. So this equation will not be satisfied anymore. So it would appear that we cannot put it into a geostationary orbit at a higher radius. But wait, supposing we tie the satellite to the surface of the Earth with a very strong cable, and there is tension in the cable. So now the equation becomes T plus gm1 m2 by r squared is equal to mr omega squared. This equation can now be satisfied for the right value of tension. And the tension will be mr omega squared minus g mass of the Earth mass of the satellite by r squared. You can see now that if I increase the radius but keep it a geostationary orbit so that this equation is satisfied, omega is still the same, 2 pi by 24-hour time period. Then as r increases, this term increases and this term decreases, but it has a negative sign. So the overall tension increases. So we would need a cable which is very strong to anchor the satellite. Suppose we do that. Here we can take m outside the brackets. So we have r omega squared minus g me by r squared. So for a given radius, and omega of course is 2 pi by 24 hours, as the mass of the satellite increases, the tension will increase. So we can actually put a platform weighing even 100 tons up there, and it'll have to be anchored by a very strong cable or several cables. Now what will the people in that city see? They will see this heavy 100-ton platform right over their heads, anchored by a cable under high tension. And as far as they are concerned, the platform is pulling the cable, which in fact it is, causing the tension. So from their point of view, which is a rotating frame of reference, this is the frame of reference of the people in the city above whom the satellite is in geostationary orbit. These people will see a centrifugal force acting on the satellite, pulling it outward, which is causing the tension of the cable. And now you can build an elevator which can run up and down this cable all the way to the satellite and back. And this elevator is what is known as a space elevator. Now using this elevator, we can fetch materials from the surface of the earth all the way to the satellite, and there on that platform start building our space-going vehicles. In order to launch a satellite from the surface of the earth and get it to a distance of 50,000 kilometers from the center of the earth, you would have to spend an enormous amount of fuel, all that can be saved on using this elevator. It will be much cheaper now to launch spacefaring vehicles from the top of the platform. Well, is this practical? Can we actually build something like this? Well, that question I will leave to the engineers. Thank you.